The biggest number on a model card may not be the number doing the work. That sounds strange because for years the easiest way to talk about an artificial intelligence model was to name the model and name the parameter count. 7 billion, 13 billion, 70 billion, 100 billion. The number became a shortcut. Bigger sounded heavier, bigger sounded more expensive, bigger sounded more capable. But that shortcut is breaking. Here is the paradox. Poolside describes Laguna S2.1 as a model with 118 billion total parameters, while activating about 8 billion parameters per token. If you only hear the first number, it sounds like a giant model. If you only hear the second number, it sounds like something much smaller. Neither number by itself tells you whether the system is actually deployable. That is the point of this episode. Model size is no longer enough, not for local artificial intelligence, not for real workflows, not when the practical question is whether the complete system can reliably finish the work. The better question is not, how big is the model? The better question is, what exact artifact are we talking about? What format is it in? What runtime serves it? What memory and cache behavior does it create? What harness has to use it? And what happens when the workflow fails and has to recover? Start with the first split, total parameters versus active parameters. Total parameters describe the full model artifact. In a sparse mixture of experts model, not all of those parameters necessarily participate in the computation for every token. Active parameters describe the portion used for a token's forward computation, according to the routing path. So 118 billion total parameters and 8 billion active parameters are not contradictory. They are different measurements. But this is where sloppy arithmetic can mislead people. Intuition. The model can contain many experts while routing a token through only some of them. That means the total model can be very large, while the active work for a single token can be much smaller than the total parameter count suggests. That is why 118 billion total parameters and 8 billion active parameters are not contradictory. They are different measurements. But this is where the conversation often goes wrong. 8 billion active out of 118 billion total is not 3%. It is approximately 6.8%. If someone is talking about selected experts out of a larger expert pool, that may be a different denominator. But the active parameter share, using the locked 118 billion and 8 billion figures, is about 6.8%. That correction matters because local artificial intelligence arguments often depend on arithmetic that sounds precise, but is actually mixing categories. A sparse model can reduce the work per token without making the rest of the model disappear. The inactive weights do not become free. They still have to be available somewhere in the memory and storage hierarchy. That is the second distinction, resident weights versus active work. Resident weights are about capacity. Active parameters are about computation. A system can have enough capacity to hold a model but still struggle with prompt processing, cache growth, memory pressure, runtime stability, or tool use. It fits is not the same as it is deployable. Now add precision format. People often say 4-bit as if it were a complete technical description. It is not. 4-bit arithmetic can be useful for intuition. 8 billion parameters at 4 bits is approximately 4.0 gigabytes in decimal terms, or about 3.73 gigabytes before overhead. That is the simple arithmetic. It does not establish the lower memory traffic figure from the video intake. Any lower effective memory traffic number would need architecture, compression, kernel, or runtime evidence. But even that corrected arithmetic is not enough. A native low-precision model artifact is not automatically the same thing as a post-training quantized conversion. MXFP4 is not the same claim as an MLX 4-bit build. An MLX model is not automatically equivalent to a GGUF conversion. A Q4 label in one ecosystem does not guarantee the same quality, memory. OpenAI's GPT-OSS 120 billion model is useful here as a comparison case, not as an acquisition recommendation. As GPT-OS 120 billion model is useful here as a comparison case, not as an acquisition recommendation. The official model card says it has 117 billion parameters, 5.1 billion active parameters, and uses MXFP4 quantization for its mixture of experts weights, with evaluations performed in that same MXFP4 format. That supports the broader lesson: the precision format is part of the model identity. The deployable unit is not just the name on the model card. It is the exact model, exact format, exact runtime, exact harness, and exact workload. This is also why memory bandwidth arithmetic has to be treated carefully. Apple's official Mac Studio specifications list the M3 Ultra with 819 gigabytes per second of memory bandwidth. That is a real hardware specification. But dividing bandwidth by a nominal active weight byte estimate does not produce a measured token rate. It produces, at best, a theoretical ceiling or an intuition pump. Real throughput depends on kernels, cache, routing, memory movement, prompt size, sampling, runtime overhead, and failure behavior. The bandwidth number is not fake. It is just not the benchmark. The same caution applies to generation speed. When people talk about tokens per second, they are often talking about decode, the autoregressive generation phase after the prompt has already been processed. Decode matters. If a model is painfully slow to generate, it can be unusable. But decode is only one performance regime. Before decode comes prompt processing, often called prefill. Prefill is where the model ingests the input context. For ordinary chat, that may be modest. For Hermes-style work, research packets, long source files, codebases, transcripts, or multi-turn tool state, prefill can dominate the user experience. A model that produces the next token quickly after the context is loaded can still be frustrating if it takes too long to ingest the context in the first place. And a model that handles a short chat window smoothly can still break down under long context pressure. Then comes time to first token, the delay between sending the prompt and receiving the first generated token. That delay includes prompt processing, runtime scheduling, cache setup, and other overhead. It is often the number a user feels most directly. Then comes the key value cache. The key value cache is not a small implementation detail. It is part of the capability of the system. As context grows, cache memory grows. If the runtime supports prompt caching or cache reuse, repeated work may become faster. But cache reuse also has to be correct. A fast cached answer that contaminates requests or reuses state incorrectly is not a win. The locked source packet includes a historical MLXLM issue where cache cross-contamination was reported under concurrency in an earlier version. That issue is closed and version specific, so it should not be treated as an indictment of every current MLX release. But it demonstrates the category of failure. High throughput can coexist with wrong outputs. There are also open issue reports around long context prefill, server crash loops, and large model memory pressure. Again, these are not universal verdicts. They are evidence that runtime behavior remains part of the evaluation. A model that loads is not necessarily reliable. A model that generates quickly is not necessarily correct. A model that survives one demo is not necessarily stable under sustained workflow use. This is where Laguna S 2.1 becomes useful as an explanatory case study, but not as a QCS model recommendation. Poolside's own public material is unusually helpful because it gives both sides of the story. It publishes the headline specifications, 118 billion total parameters, 8 billion active parameters per token, mixture of experts architecture, and very large context. But it also describes limitations in third-party harnesses, including difficulty with tool schema definitions in Hermes Agent's terminal tool, invalid nested tool calls, and overthinking in some settings. That is the whole episode in miniature. The model size number looks impressive. The active parameter number explains why the compute story is more subtle. The harness limitation explains why neither number is enough. If the model cannot reliably follow the tool schema, recover from mistakes, manage long context, preserve cache correctness, and complete the workflow, then the parameter count did not tell you the real cost. The runtime is part of the model. The harness is part of the benchmark. The recovery behavior is part of the capability. This also changes the economics conversation. The weak argument for local artificial intelligence is the simplistic hardware payback story. Buy a machine, divide by token prices, declare victory. That is not source locked here, and it is not the strongest case. The stronger local value proposition is control. Local artificial intelligence can matter because it can give you privacy, continuity, reproducibility, provider independence, predictable availability, pricing, latency, routing, or access. Those benefits are operational. They are not automatic. They matter only if the local system is reliable enough for the work. That is the new standard for deployable capability. A local model is not deployed when it loads. It is not deployed when it answers one short prompt. It is not deployed when it posts an impressive decode number. It is deployed when the complete system can repeatedly finish the work under the constraints that matter. Model size used to be a rough shortcut for capability and cost. Now it is only the beginning of the question. The future of local artificial intelligence will not be decided by the largest model that fits in memory. It will be decided by the smallest complete system that can reliably finish the work. Subscribe for more evidence. First, artificial intelligence infrastructure analysis.